Okay, Math 20, I just want to have a look at the first lesson here for radical expressions and equations, radical review. So this will largely be Math 10 review. There are a couple of new sort of concepts there. So all of the formulas from Math 10 that we sort of need to have fresh in our brain include product of powers, quotient of powers, etc. I'll sort of review them as we go here. Okay, the perfect squares and the perfect cubes. Okay, these are the perfect squares, right? The reason these are perfect squares are, of course, because these numbers can be, can create a perfect square, right? If I gave you 25 blocks, or let's just say 9 for easier numbers, if I gave you 9 blocks or 9 square Lego blocks, you could create a perfect square with those, right? A perfect square, being, you know, a 3 by 3, okay? That's a perfect square. So our perfect square number is the 9. The 9 is the perfect square, okay? And then I know that my root is the side length. So if we think of that like that, 9 would be our perfect square. A perfect cube, the classic example of a perfect cube would be the Rubik's Cube, okay? The Rubik's Cube, of course, is the shape of a cube. Whoops. No, that's fine. Okay, and then of course, if you think about how many blocks would be in, how many little mini cubes would be in that big Rubik's Cube, there are 9 in each layer, right? There would be 9 and 9 and 9, so that's 27. And the cube root of 27 is of course 3, which means we've got 3 by 3. So when you consider the Rubik's Cube, that's the perfect square, perfect cube rather, which is 27, okay? So we should be familiar with, I would say, the perfect square numbers and the perfect cubes, probably up to and including 5 cubed, 125. Those are probably the ones we should have memorized, okay? And then, of course, the ones after these are them, but I don't know if you have to memorize those. I don't even have 14 cube memorized, so anyway, that would help for this unit. So if we look at radical review, let's just look at these first 3 laws. This first law is called the product law, which means, right, when we multiply, we get a product. So if I'm looking at multiplying 2 powers with the same base, we add the exponents. So a perfect example of that is this one down here, 2 cubed, which is 2 times 2 times 2, 2 to the 7, 2 times 2 times 2 times 2 times 2 times 2 times 2. And of course, I'm writing like a giant. Let me move that over. And when I do that, I get, of course, 2 to the power of 10. Okay, so we know the shortcut there is just to simply multiply those 2 exponents, or sorry, add the 2 exponents. When we're multiplying 2 powers of the same base, we add those 2 exponents. So 3 plus 7 is, of course, 10. And if we understand that, that's not hard. It's when you kind of start falling apart, right? We're just expanding 2 cubed and 2 7, that's 2 to the power of 10, okay? And it doesn't say to evaluate, it just says to simplify. So we don't have to find the actual value of 2 to the power 10. And same with this next one. This is quotient law because we're coming up with a quotient, which means when we divide, what's our answer? So this is 3 times 3 times 3 over 3 times 3. And of course, what happens here is our 2 3's on the denominator cancel with 2 3's on the numerator, and we're not getting 0 there, we're getting 1. Keep in mind that that's 1 because 3 divided by 3 is 1. Okay, and therefore our answer is just 3, or 3 to the power of 1, little invisible 1 there on our exponent. And so the shortcut there is to do 3 to the power of 3 minus 2, which is 3 to the power of 1. And then we've got this negative exponent law, okay? And if you look up here, the negative exponent law simply says that if I've got a to the power of negative x, that's the same as 1 over a to the x. A little review of Math 10 to see sort of where that comes from. If I do like 2 cubed, I get 8, 2 to the power of 2, we get 4, 2 to the power of 1, we get 2, 2 to the power of 0 is of course 1, anything to the power of 0 is 1, 2 to the power of negative 1, if I follow the pattern, what's happening here, so just in terms of patterning, I'm dividing by 2, dividing by 2, dividing by 2, and so on. And so 1 divided by 2, this has to be 1/2, okay? Or 2 to the negative 2 has to be 1/4. So another way to think of the top here is we want to simplify. I'm still looking at a product law here, 3 plus -6. So this is 4 to the power of 3 plus -6, which is 4 to the power of -3. And then I need to take the I need to take the reciprocal, move this numerator to the denominator in order to turn that into a positive exponent. So that would be 1/4 cubed. Okay, that's question C. So hopefully that's a fairly decent review of Math 10, or hopefully you remember that. In terms of terminology, the little outside number here is called the index. The radicand is the value underneath the radical, and the whole entire thing is called the radical. Okay, and then multiplication property, we've seen this a little bit. This is something like if I said like the square root of 8, okay, there's a little invisible 2 there, and that can be rewritten as the square root of 4 times the square root of 2. And of course we could simplify that because the square root of 4 is of course 2 root 2. So that's just saying that you can split up the factors of a number into, like 8 can be split up into 4 times 2. Okay, if we want to convert from mixed to entire radicals, what I want to do is I want to look at how can I make this 7 pop underneath the radical sign. Well, I can't just put it under because 7 is not equal to root 7, of course. But what I can do is I'm basically saying what is, what number, the square root of what number would give me 7? Some of you can right away tell me that the square root of 49 is 7. If you're not sure, you can plug that in underneath the radical and you're going to multiply 7 by itself 2 times. Why 2 times? Because there is a little 2 here, right? There's a little invisible 2. So it's 7 squared times 2. That's 49 times 2, which is the square root of 98. Okay? Same with this one. The square root of what number or what value gave me a to the 4? If I want to put that in, I need to square that. So that's going to be the same idea except with letters. I'm going to go a to the power of 4 times a to the power of 4. And then there's an a already underneath my radical. So that's going to be the square root of a to the power of 9. Alrighty then, let's go to the next one. Again, whatever I put underneath the radical has to be squared normally. Actually, this time it's not going to be squared. This time it's going to be cubed, right? If I've got 2 cube root 2, what would I do to that 2 to put it underneath? I would have to cube it. So that would be equal to the cube root of 2 cubed times 2, which would be the cube root of 2 to the power of 4, okay? Because 3 plus 1 is 4. So same idea here. However, we've got some variables as well. So let's just take a look there. I want to cube, right? This is the cube root, so I want to cube 5. It's going to be 5 cubed, b cubed times 3b squared, which is already there. So that's 5 cubed, what is that? 5 cubed, 5 times 5 times 5, 125 times 3. So that should be 375. Okay, that's the cube root of 375, b to the power of 5. Okay, so if you half get that, then why don't you try these your turns and just pause the video, give it a try. You're better off to give it a try and get it wrong than to not try it at all. So give the video a pause and try those 3 questions. Okay, so hopefully you were able to get the same answers here. If you need to pause the video and check your work, that would be great. And now let's move on to number 3. Convert entire radicals to mixed radicals. Identify any restrictions on the values for the variables. So this first question, 3a, there are no variables, so I don't have to worry about the restriction component here. Okay, I want to read this carefully. Identify any restrictions on the variables, on the values for the variables. So if I look at the first one, the 200, I want to convert that from an entire to a mixed radical. So some of you, if you want, here's the shortcut version. Largest perfect square factor of 200 is 100 times 2. So the square root of 100 is 10 root 2. And the sort of fail-safe way is to, of course, take 200 and break it into a factor tree. We might do 100 times 2, and then 25 times 4, which gives us 5 times 5, and 2 times 2. So another way to have done this question is to rewrite this with all of our prime numbers. We're using the prime factorization of 200. And then, of course, how many 2's can I take out? I can take out a single 2 and a single 5. And then I've got 2 times 5, and I'm left with the root 2 under the brackets, under the radical, rather. So that's 10 root 2. Okay, so that's another way to do this question if you were unable to see right away that the 100 is the largest perfect square factor. Okay, let's look at the next question, B. So what I want to do is, similar to this concept where I'm using the prime factorization, I can do the same thing with the C. So I'm looking at the fourth root of C times C times C times C 9 times. And of course, how many fourth root of C's do I need to take out a whole C? Because this is a 4 here, I would need 4 whole C's to take out a complete C. So I can take out 2 C's, so I've got C squared times the fourth root of C. Okay, and similar to 48, the shortcut for those numbers would be to take the largest perfect square factor here, which would be 16. 16 times 3 is 48, so I can go 16 times 3, and then y to the 5, y, and of course the square root of 16 is 4, and when I look at my y's, I can take out a complete y here, another complete y, so we get 4y squared, and what we're left with underneath the radical is the square root of 3y. Okay, so there's those 3 questions. Why don't you pause the video again and give your Okay, so hopefully you got these same answers as me. Couple quick things. I just realized as I was doing this that I forgot to identify the restrictions on the last question, and I think there's even a question like that on the prior page. So we're just going to hop back there and do those restrictions. So let's talk about restrictions on variables. What the heck does that even mean? All right, when we talk about restrictions on variables for radicals, I know, for example, that I can take the square root of 16, and that is 4. But can I take the square root of negative 16? Indeed, I cannot. Not possible. And that's because there's no number that I can multiply by itself twice to give me a negative 16. Okay, my index here is even. Okay, so I cannot have a negative under an even index. Okay, can I have a negative under an odd index? If we take an example such as, let's just pop it into the calculator here. If I do like the cube root of negative 8, that is of course negative 2. Okay, the cube root of positive 8 is positive 2. But I can also take the cube root of a negative, because negative 2 times negative 2 times negative 2 is negative 8. So indeed, I can take a cube root of a negative as long as the index, right? I can take the root of a negative as long as the index is odd. Okay, so let's just take a look. Here's an odd index. So if there's an odd index, there are really no restrictions. Okay, if there's an even index, there are restrictions. My number here underneath the radical has to be, the number must be greater than or equal to 0, right? We can have the square root of 0, which is 0, But as soon as we go into the negative values, we know that this does not work. So for this, because I've got a square root here, my index is even, we would say that j has to be greater than or equal to 0. Okay, because we have an odd index here, odd index, no restrictions. Okay, on k. If we look at this question here, we have an even index, okay, even, so therefore c must be greater than or equal to 0. Okay, even index, y must be greater than or equal to 0. So those are the restrictions. Let's look at the your turn ones down here. Even index, m must be greater than or equal to 0. Even index of 2, n must be greater than or equal to 0, and p must be greater than or equal to 0. Okay, compare and order radicals. 5 bentwood boxes, each in the shape of a cube, have the following diagonal lengths in centimeters. Okay, whatever. Order the diagonal lengths from least to greatest without using a calculator. So I would want some evidence that you understand this. Of course, we can, our calculator's probably with us, but what we want to do, the easiest things to do here, if we didn't have a calculator, we would change everything, change to entire radicals. Okay, how to do that? Let's look at h root 3 first, because we'll just review this 13 to the 1/2 in a minute. H root 3, that is of course as a radical, we would change that to the square root of 8 squared times 3, which is square root of 64 times 3, which would be the square root of 192. 14, that's the same as the square root of 14 squared, which is the square root of 196. The square root of 202 is already done, okay? And 10 root 2, that's equal to the square root of 10 squared times 2, which is the square root of 200, right? That's the very first question we did up here somewhere. I think we did that one. Didn't we do that one? Right here, yeah. 10 root 2 is the same as square root of 200. This 4 times 13 to the 1/2, if we can recall, if I have something like 2 to the 1/2 times 2 to the 1/2, that's the same as 2 to the power of 1. And I also know that the square root of 2 times the square root of 2 is also equal to 2 to the 1. So where does that come from? That's because the square root of 2 is equal to 2 to the 1/2. And if you remember this from Math 10, what we do is this little tiny denominator here, the denominator becomes the index, and this numerator would become the power here. So for example, I could do something like 8 to the power of 2/3, and the denominator, right, the denominator becomes the index, so that would be the cube root of 8, and then the numerator here becomes the power. Okay, so this 2 here would go here. And it could go either inside the brackets or outside the brackets, okay? I would put it outside because I can do the cube root of 8 in my head. Cube root of 8 is 2, and then 2 squared is equal to 4. So this value here is just actually equal to 4. You could always plug that in our calculator as well. So what this one here means, let's just go back to this 4 times 13 to the power 1/2. This means 4 times square root of 13, and then of course we want to change that to an entire radical. So in order to change that to an entire radical, we are going to do 4 squared times 13, which is 16 times 13, which is the square root of 208. Now we've got these all in the same form, so it's easy to see which one's the smallest here. So from smallest to biggest, I know that, what do we have here? 192 is the smallest, so that would be 8 root 3, okay? And I'm going to go, that's 8 root 3, okay? This one's the smallest, and the next biggest would be the 196, which is 14, and the next biggest would be, of course, 200, which is 10 root 2. And then the next biggest would be the 202. And then the last biggest would be the 4 times 13 to the 1/2. Okay, so there's our answer there. Okay, and if you were to try the last one, if you wanted to try that on your own, that would be fine. Okay, so here's our answer there. Hopefully that was not too bad. And the assignment booklet, I would definitely do questions number 1 to 5 and number 6 if you are a keen bean. Okay, if you're a keen bean, try number 6. Okay. Anyway, that's it. Have a good weekend, and if you have any questions, please do not hesitate to ask me in the next class.